Okay, so let's make a start. Welcome to today's seminar. Today we have Ignacio Trujillo, which I guess all of you know, so I'm not going to give him a formal introduction. But Nacho is a staff astronomer here at the IAC, and he's worked on a number of aspects, a large number of aspects of galaxy formation and questions in astrophysics in general. And today he's going to tell us about a faint glow to trace dark matter.
Okay.
Away, Nacho.
Thank you. Can you hear me? Okay. Yeah, so today I'm going to talk about the result that I have been working on with Mireia Montes. Mireia is the leading author. This is a result that we have published recently in Monthly Notices. And it's about finding a way to see whether we can see somehow the dark matter, no? Just using the light of some emission, either X-rays or in this case I'm going to show you stars. So the first slide, of course, is can you turn a little bit off the lights so you can see better the images? So you have to see dark matter, yeah, right. So okay, that's fine. That's fine, I think. Well, that's fine. You will see more dark matter. Okay, so this is the paradigm. We have good reasons to think that we are surrounded by a huge amount of matter that is called dark matter, although I think the right terminology would be something like invisible matter, because it's matter that, as far as we know, is not emitting light. So it's not either dark, white, or red. It's simply invisible matter. So the paradigm tells us that we are surrounded by a huge amount of that kind of matter, and that matter is a structure, particularly today. It's quite a structure in a filamentary way. And at the densest spots of that dark matter, we find the stars, and consequently, we find the galaxies, and we see that nodes of the large scale structure. So the main motivation of this work is whether we can see somehow all these structure around the galaxies and somehow being able to see such dark matter. We have focused in a particular aspect of the large scale structure, which are the galaxy clusters, in particular the most dense clusters. This is a picture. On the left, you can see how a massive galaxy cluster is seen when you can see the dark matter. So this is a simulation. So you see the main galaxy, the main central galaxy. Then you have other other large galaxies as well. You can. Do I have a pointer, Mike? Is this a pointer? Yes. Maybe because this is not even working. No. Maybe there. Because the problem that I have is even with the mouse you cannot see what I'm. No, because it's not. See? Okay, I go ahead and then if you can find. So. Around the main galaxies, you can see a huge halo of in the simulation, which correspond to the dark matter. No? However, when you see the galaxies, so this is also a very massive cluster, you only see the galaxies, and you don't see such a huge envelope of dark matter that you would expect. So the idea here, what it has changed in the last few years, is that instead of having this kind of nice images where we only see the brightest part of the galaxies, now we can move to much deeper images. So this is the same, whether I have played a little bit with the contrast. And now you can see that surrounding the main galaxies, there is a very faint but very extended contribution of light that it starts to have a different shape than the main galaxies itself. So this faint halo around the main galaxies is what is so-called the intra-cluster light. And the main result of this talk today is to show that the intra-cluster light and the dark matter in galaxy cluster are distributed very, very, very similarly, up to a level of similarity that we think it's indicating that both components are basically distributing fully the same. So to understand this better, I'm going to show you a movie which is the formation of a galaxy, very massive galaxy clusters in redshift 2 or so. So we are observing the last 9, 10 giga-years of evolution, and you can see that the dark matter it's collapsed, so the main halos of dark matter are collapsing, and you can see that within that collapse, a huge amount of dark matter is stripped away and forming a structure that not necessarily correspond to the same symmetry that you're observing in the center. For example, look at those tails that are moving ahead. No? So they are forming a very rich structure that particularly today at redshift 0, it's what is from this envelope that is more circular, no? More spheroidal. So if we make the same exercise, but this time concentrating on only the stars, so this is again a cosmological simulation, but the authors here are only showing the stars. So the halo of dark matter is already there, but they have not showing this on the images. I'm showing you to this also for you to see how the distribution of stars is also quite affected, and when the galaxies are falling into the cluster, they also get very affected by the effect of the tidal forces, and also you can see that the stars of the outer part of the galaxy begin to populate a distribution that is not longer associated to the individual galaxies, but as the whole structure itself. Thank you, Mike. That's much better now. Okay, so these are the galaxies, and when they are, when I'm moving forward the time, you can see that all these stars that before were only in the particular galaxies are now populating the huge structure of the cluster. At the end of the simulation, you can see, I'm going to put it again, you can see that the distribution of those faint stars that form the intra-cluster of, it's very, okay, here. You see that they populate very similar to what we have seen before as the dark matter. Okay, so we have a good theoretical reason to think that both components should trace the same gravitational potential. Now, what we would really like to do is to see whether this is observed. We also make a quantification of the agreement between the two components, the intra-cluster light, that is something that we see, and the dark matter, that is something that we think is there. So what we have done is to use the Hubble Frontiers Fields as the data set. The Hubble Frontiers Fields is an initiative of the director in the Hubble Space Telescope. So they decide to allocate a lot of time with the Hubble to 6 different clusters, and which go from redshift of around 0.3 to redshift a little bit above 0.5. And the idea why they decide to put a lot of observational effort with the Hubble there was because they were interested on the primordial galaxies, redshift 9, redshift 10 galaxies. They used these clusters, these massive clusters, as a lens, and using this gravitational power, they try to find the primordial galaxies, okay? So that was a huge observational effort, and as you can see, the declination goes from quite in the south to also quite in the north, so you can, so people interested in both hemispheres can make a follow-up, okay? So this is the amount of integration that they put in each cluster. So you can see that they allocate a total of 140 orbits, either using the optical camera and also the near-infrared camera. So they spend a huge amount of time. Such a huge amount of time is equivalent to be the second deepest ever observation of a spot in the universe after the Hubble Ultra Deep Field. So you can have an idea how deep these images are. So these are the 6 cluster they observed. So as I told you before, they were interested in particularly on observing the gravitational enhanced very faint spots, so galaxies at redshift 9 or so. But taking advantage of these super deep images, what we did was to explore, as I said before, these faint envelope that are surrounding the main cluster, okay? So in some occasions, this is not at all straightforward because, for example, in this cluster here, the cluster that we are interested in are these galaxies, but sometimes you have huge foreground galaxies that are making your life much more complicated, and then you have to mask and make all kind of tricks to avoid the contamination of this kind of light. So the observational data came from here. The dark matter maps came from other people. So because, as I said before, these galaxies were very interesting for observing high redshift galaxies, they asked to the community to provide the gravitational lensing maps so people can see where in the map, where in the images you would expect to find the most lensed galaxies, so you can look at there and identify those very high redshift structures, right? So up to 6 different mass models were computed to understand the location of the dark matter in these clusters. In particular, this is the first cluster that I saw you, well, this cluster in particular, okay, the Hubble 2744. And you can see here in red the magnification lines. In blue is the mass models that they recover, so they include the stars and also the dark matter, okay? So at the location of the galaxies is basically the baryonic matter, but in the outer part corresponds to mass that is dominated by the dark matter. And also in green you can see the image of the galaxies. So you can see that although you have galaxies outside in the outer part of the galaxy, the dark matter mass is more concentrated towards where you can see the main galaxies, right? So once we have the mass models or the mass maps of every cluster, and we have also the super deep imaging, it's straightforward to make the contours and see whether they look alike or not. So this was the exercise that we did. So in green, you have the intra-cluster-like contours, and in pink, you have the dark matter contours according to the mass models, okay? So here was this is a very soft, gentle distribution of light. So here, it's easy to see that they are very similar. In more complicated pattern, you still see that they look quite alike. And this is also that you can see in all the galaxies. This is a nightmare, as I said, because of the contribution of this foreground galaxy. And here you have bright stars and so forth. But in the regions where we can make the job, you can see that the contours looks very much the same. So that is encouraging because they look quite similar, but you would really like to make a step forward and try to quantify this a bit more. At a fixed distance. So we define at a given distance, as I will show you a little bit more about that. Okay? And then you look at the shape of the contours. In fact, this is the key thing now. So this is just for visual say approach to the problem, but now let's make a quantitative approach. So how do you study when you have two different contours, whether they look the same, similar, or not? Well, it turns out that people in the literature, particularly people interested in shape matching, for example, in pattern recognition, are two faces the same or not? They have developed several metrics, but in particularly we use one that is quite simple to compute, which is the house door distance. The house door distance is the following. So you take two sets of data, for example, this green contour and this blue contour. So for each point of the blue contour, okay, you estimate the minimum distance that you have from one point to another point on the other set. You move to another point and you make the same. And once you have done this for all the points in the blue contour, you take the maximum distance that you find. You do the same for the green set. You look for the minimum distance for each point, and then you take the maximum value. And the maximum of the maximum value is what you call the Hausdorff distance. And this is what we use. Okay? We measure that value. So the point is, instead of using directly the Hausdorff distance, we use a modified Hausdorff distance, which is more robust to having outliers, because we don't have in images, and so you have a lot of spots that you cannot trace because you have a star or so. So you have to use something that avoid this kind of problematic, and that's why we use the modified Hausdorff distance. But the idea is the same: take the maximum distance between two sets of data, the maximum of the minimum, to characterize how two contours are alike. And these are the quantitative values. So, in red, we saw, as a function of the radial distance, the maximum difference we find between the intra-cluster light contours and the mass contours. So you can see that, for example, in Hubble 2744, which was this cluster, okay, as soon as we are moving away, we find that the maximum, the modified Hausdorff distance grows from a little bit of around 10 to something like 40 kiloparsecs. So these are the red dots. So that corresponds to a typical distance between the contours of the intracluster light and the contour of the mass model of the order of 40 kiloparsec. 40 kiloparsec is, for you to have an idea, the size of the Milky Way when you go to the very outer region. So the typical difference between the two sets of data is the typical distance of the order of the Milky Way, so it's quite similar. But of course, you can say, that's fine, but how do I know that this is more or less the same that the matter? So I define a distance. So this distance, this is your question. Just using so you go through all the points to the contour, as I said before. So in the case of the intracluster light is an isophot, okay? In the case of the dark matter is the aniso density. Mm-hmm. Do you mind to make that question at the very end? So I have a slide prepared. So just for the moment, just believe that is fine. So let me follow with the story, okay? So now the question is, how representative is this of the, so when I say the typical distance between the intracluster light and the dark matter is of the order of 40 kiloparsecs, this is too much or is not? So what we can do is to make the comparison of the 6 maps. So we can take the contours of the 6 maps and see what is the typical distance that they have been able to reconstruct based on the same lensing, okay? So how the different teams agree on reconstructing the mass map of the cluster, okay? So this is represented by this bar. So this is the difference they find. So what we are basically finding here is that because the intracluster light is going through the isodensity contours that they are able to reconstruct, so the intracluster light is as a good indicator of where the mass is as they are able to do with the present technology. So they cannot improve. So far, the better they can do is when they compare the different mass reconstruction, is distances in between them that they are of the order of the distance between the intracluster light and the mass. So that's a key thing. So as far as the data is and the technology reconstructing the mass of the cluster is, we find no more distance between the intracluster light and the mass that the people reconstructing the mass itself. Okay? So in that sense, the intracluster light is going exactly as well as you would expect. So imagine that in the future they are able to agree much better in the reconstruction of the mass map. Then maybe they can find difference with respect to intracluster light. But so far, at this level of technology, the intracluster light is distributed as the mass map at such a level of accuracy. So as better as they can reconstruct. And this is something that we find in all the clusters, as I will show you now. And in green, what I'm showing here is what would you expect if instead of having patterns that are complicated with different shapes, you were comparing with something that is perfectly circular, okay? So when these points deviate quite significantly from these points, that means that the cluster that we are observing deviates significantly from the perfect circular symmetry. So these are two clusters, these are another two clusters, again the same story, and these are another two clusters, again the same story. So you can see that we always find of the order of maximum distance of the order of 30 kiloparsec between the intra-cluster light contours and the typical mass distribution. So at this very moment, I hope I have convinced you that quantitatively the contours of both the mass, the dark matter, and the intra-cluster light are very similar. But then you can say, that's fine, but we know that the main contributor to the baryonic mass in clusters are not the stars, but the X-ray. So is X-ray also a good indicator of where the dark matter is? And as most of you know, the answer is no, because this is not the Bales cluster, but another one, but it's the same story. So because a cluster of galaxies are very active and very alive, and they are colliding all the time, so groups are infalling, and we have a lot of interactions there. So in this sense, because they are not quiet and living peacefully, all this substructure is resembled on the location of the X-ray and the matter. For example, this blue distribution here corresponds to where the most of the mass in the cluster is, and in this red light here corresponds to where is the emission of the X-ray, so where most of the gas is. This cluster is the rest information due to a collision of two subclusters, which are one here and one there. The galaxies and the dark matter has gone through each other basically without feeling the interaction just gravitationally, but the gas has mainly collided here and formed this emission of the gas. So we know that the vast majority, for example, in this galaxy, the vast majority of the X-ray is at a different location where the mass is. So what we have done is to take also a very deep observation in X-ray of the cluster, of the 6 clusters we have been studying, and see how different is the contours of X-ray emission compared to the mass and the intra-cluster light, just to see how different they look. So here again are the contours. So this is the intra-cluster light, this is the mass of the cluster, and this is the X-ray. So you can see that in this particular case, the X-rays are emitting far away from where the location of the main galaxies are. Here, for example, the X-ray are more or less at the same location. Here is again quite different. Here is relatively similar. Here, which we thought is going to be very much the same because the cluster looks relaxed. Also, the X-ray is offset towards the upper corner, and here they look more or less the same. So you can see that in some clusters it could work, but in some clusters that are very active, it's not working. So here you have again some comparison. When you have, for example, here the X-ray emission mostly located in this region, you can see that the distance, the Hausdorff distance, is very different from. So this is the comparison between the intra-cluster light and the mass, as I showed you before, and this is the X-ray versus the mass, and you can see that the distance, as you expect, is much more farther away. So in some occasions, when the X-ray and the stars and the mass are more or less similar distributed, you can see that they look the same, but we have found always systematically that the intra-cluster light show distances that are smaller than the typical distance that you find using the X-ray. So here I show you another two examples. These clusters and the last two clusters, and you can see that only in this case you find that X-ray and intra-cluster light more or less trace similarly the dark matter contribution. So this is the main result of the paper, and I want to show you the possibility of 3 future developments and why this could be interesting. So the very first thing is, of course, to go to another clusters where the dark matter has been mapped following the gravitational lensing and confirmed with deep imaging that in fact what we are finding with intra-cluster light is also visible, no? So that the distribution of the intra-cluster light and the dark matter is very similar. And also we would really like to go much farther away, because so far we have been able to go only to 150 kiloparsec away. We would really like to make it at 200 or 300 kiloparsec distance, where we definitely would be living in a regime where the dark matter should be contributing completely, no? The problem that we have so far is that the size of the camera, of the wide field camera 3 of the HST, is not very large, okay? So the reduction is difficult, and normally the intra-cluster light is subtracted because of the small field of view. So you really would like to make this in more larger areas. Then imagine that this is confirmed for more clusters. Then, of course, if you think that the intra-cluster light and the dark matter distribute similarly, it's relatively straightforward to now make deep observations of not only a few clusters, but hundreds of clusters, going far away to characterize the intra-cluster light, okay, and make a direct comparison between that distribution of the intra-cluster light with the lambda CDM simulations and see whether they look similar or not. And if you would like to dream, then we can even explore something more exotic, which is, so if we can prove that the intra-cluster light and dark matter behave similarly, then we can go into the details, okay, and try to see whether we can infer some properties of the dark matter particles. For example, this is the same simulation using the standard cold dark matter, and this is using the same set of simulation, but this time allowing to the dark matter particles to interact themselves with a new type of force, the fifth force that we don't know anything about, the dark force. And if there is a dark force, that implies that the dark matter will not longer distribute exactly as the stars, because the stars would not feel such an interaction, and they will slightly distribute differently, okay? So if we were able to go to such a level of detail, we would be in position to start to make inference of any kind of dark force also. Of course, this is a dream, because from the observational point of view, I think that we are very far away from even finding a small kind of difference. Okay? So my main conclusions are, as far as we have been able to see, with 6 clusters, intra-cluster light and dark matter are equally distributed at the level, at such a level that, as the level that the mass reconstruction of the cluster are able to give us. So when we take different mass reconstruction, intra-cluster light distribute exactly the same. And I think I put it here like that, so one can use the intra-cluster light to see where the dark matter is distributed. It's not the dark matter, but because it's following the same kind of gravitational potential, the same structure, we are allocating stars at the same position where the dark matter is dominating, and somehow, when we see a beautiful image like this that I saw from Javier in Coma, this small and soft envelope is somehow showing us where the dark matter is. Thank you very much.
Thank you, Nacho, for telling us about this very
I
exciting
have
result.
the very first question, I think, is one of yours. No? How do I define the distance, right? Or the contour? We have
question
found.
was, how do you choose the two contours to be compared?
Okay, there's nothing like, yeah, so let me show you. So here we have, okay, so Jorge, you are asking me why I select 50, 70, 100, 130? No. Okay. Okay. Okay, maybe this helps you. So, the very first thing that you need to do is to identify what is a center. Okay? To a contour, you have to identify a center, an ellipticity, and a position angle, basically. Okay? This is but let me show you how this is working. So what we do here is, when we have two massive galaxies like this, what we do is to identify, for example, in the case of the intra-cluster light, no? So when we have a very massive galaxy, we just take that galaxy as the center for the intra-cluster light. But when we have two galaxies that we cannot differentiate which one is the most important one, or even three or whatever, we define multiple centers. For example, here we take the center of this galaxy. Here you see this galaxy and this galaxy, which are the two dominant ones. Then we take the structure and we determine the position angle and the ellipticity of this object. And then we make these elliptical contours to grow. When they collide, we just use a single one. Okay? So for example, in this region, this would correspond to a distance from the centers of 200 kiloparsecs. And here, so this is a code in color indicating the location of these elliptical contours. Okay, now we go to the point. So once I have the elliptical contours, I can retrieve in this case, a super brightness profile, right? This is the super brightness profile that you will retrieve using these elliptical contours. So once I have those elliptical contours, I can infer the super brightness at the location that I'm studying the cluster. For example, 50, 75, 100, 125, and 140. We are limited by the size of the field of view. And these correspond to these green contours that you can see more or less follow the same shape, but they have their own irregularities, okay? Okay? So this is just a way of defining a value to a distance, but then this can behave as they want. Normally they will behave similar to what we have been exploring, but in principle they would be able to do whatever they want. The same is done for the mass maps, and the same is done for the X-ray. So once you have, for example, in this case, let's look at this. This is 50 kiloparsec, okay? So we take, so at the 50 kiloparsec, you expect a brightness of 23.5 magnitudes per square second, and then you look into the image for the location of the 23.5 magnitudes per square second, which correspond to this. Okay? So we extract the same profile with the same idea, the mass map, and we compare the corresponding value of the mass density at this location, and this is the comparison. It's at the same distance in terms of these contours, but of course it depends. For example, not necessarily the mass map are always, the peaks of the mass map are always at the same location, right? Than the stars. So if they are slightly offset, we allow for that as well. But we have a study also fixing the sinks and so forth. Qualitative is the same.
Is it working? Does this have any effect? the microphone? Okay. So I had two questions. One of them was that when you have the mass map of different models, so that you showed one of them of left side of the screen. So how do you model to find the one that you want? And so this is the first question. Then the next question.
Mohammed, let me see if I understand you well. So these are the magnification lines, okay? The reconstruction of the magnification lines. In blue are the mass models. They are not exactly the same, but they look more or less similar.
Yeah, so you
No, we make the intra-cluster light is a unique set of data, okay? So we compare the intra-cluster light with each of these mass models, and that's then we take the exactly. Okay. That's the error. This is where the error bar is coming from.
Yes, okay, thank you. Yeah. So then my second question was when you define the threshold for tell too much, but I kind of see like patches of the threshold, so say islands and contours, right? So
Yes.
so these will affect the calculation.
Yes. Yeah, but no, that we put it as well. So this making your life more complicated, but this is part of the contours. So.
Okay, because that maximum distance.
Yep.
Estimating. So just a little bit.
also on the analysis method, what is the problem really to do a two-dimensional analysis, pixel by pixel? I mean, cannot you do make a mass to light ratio map?
Yeah, but then yes, you can do it. Yes, yeah, this is a good question. And in fact, some people have emailed us asking whether we can make a direct comparison, as you are saying. So, because we can make a reconstruction of the stellar light, the mass of associated to the stars, and the mass associated to the dark matter, and explore, for example, the ratio between the two as a function of distance. We have not done that in this paper. In principle, we can do it, but what I can tell you is that the difference is not at all constant. So as soon as you're moving farther away, the mass to light, the dark matter mass over the mass of the baryonic of the stars is growing. Okay, so in other words, the superbrightness profile is the steep of the superbrightness profile is much decreased faster than the mass of the dark matter.
Some questions.
Mhm.
So I have a couple of questions. One is more on the theoretical argument. You
Mhm.
basically saying that the stars, because they are collisionless, they should be tracing the dark matter distribution as well.
Which is collisionless as
Yeah,
well.
exactly. But then the thing is, the stars are constrained from galaxies, and then basically these stars will retain the orbits and retain part of the distribution.
That's right.
Unless the relaxation line is going to be
Yes.
short. So you comment on that.
Well, it's absolutely a good question, and the reason why I think that even in the future, if we were having excellent dark matter mass and so forth, that streams that you are talking about, let me show you again the movie, okay? So this is the movie of the intra-cluster light. So, for example, when the collisions appears, these kind of tails that you see here, definitely is not tracing the dark matter potential as well. So you will have to make this evolve a little bit to have now all these stars that were before in a tail now sufficiently relaxed to start tracing the entire dark matter distribution. So this is a global analysis. If you go to the details, probably then you will start finding a small detail. That's right. But the point is that the time that take the gas to get fully relaxed is much more large than this. So in that sense, it doesn't help. And in the second point is that clusters are very alive, so they are very active, and they are continuously accreting galaxies and subgroups. So in that sense, it's something that you don't. So it's fine, but it's not the ultimate thing to look for the position of the dark matter. No, we haven't think about that because I have been showing you the nice pictures and so forth, but when you put into the real pictures the mask and so that you can see in the paper, okay? So this is just a general talk. I don't want you to go into into the huge amount of details of the analysis. But for example, you can imagine that the mask is here enormous. Here is also enormous. It's very patchy, so all these galaxies doesn't pertain to the cluster, okay? So you have to go cluster, so galaxy by galaxy, making mass to be aware that you are not contaminated by so in the end, this is an image full of small holes. So it's complicated. Definitely, I mean, this is a pilot project, so I think it's quite encouraging that this is working so well, so to make it in more and more clusters just to see how far we can go. I'm particularly very excited to go very far away, you know. This is something that I really would like to see.
Well, my question goes in the same line as in Nacho. So if your clusters are not realized, the they have a lot of substructure, as you can
Yes.
see in your pictures.
Uh-huh.
How can you say that you are tracing the dynamical potential of the dark matter? Or in other words, have you studied the substructure, or what are you really tracing is some kind of bias in the way the mass models are created?
Well, this is a good question, Jairo, because one can say, well, these people have basically followed the light, and then you're basically comparing light with light. But this was only the case for 3 of the mass reconstruction, where they were putting the weight into the light that we are observing, right? In the other, I'm showing you only here 5, but in fact there are 6. So in the other 3, they were not making any kind of assumption, but just reconstructing the mass based on the gravitational arcs and the lenses. Okay, that here, for example, is very clear. You see, it's plenty. And even in those cases, this was working very well, because you can see that they basically, using very different modes, they reconstruct something that looks very much the same. So how secure I am that this is not comparing light with light? As secure as I am that they are doing a good job. So if they are making a bad job, this is nonsense. But that's why I'm saying that this is necessary. We need necessary to move to more clusters, different people, different techniques, and definitely to go much farther away, just to be sure that this is not fully dominated by the light of the stars. Okay? But numerical simulations, it would be great. It would be great as well. That definitely. That would be really good. Yeah? Mm-hmm. We contact with. That's a good point. We contact with Vicent Gillis in Valencia, because he was running. So he was running since with. The problem here, Mark, is the following. So you need to make a cosmological simulation as good as to be able to follow the stars that you are stripping from the galaxies. Okay. It's not only that you are following the dark matter. You have to be able to also model very accurately the stars within the galaxy that you are putting into the gravitational potential. In that sense, so most of the cosmological simulations that we have at hand are not able to go to such a level of detail. So I don't know whether Claudio is here or not, but in principle, they are also doing such a kind of simulation. So in the future, what you are doing is something that it would be feasible to do. But we need to be sure that they are modeling well the stars in the galaxy.
Very nice talk. I think the way to understand why the relationship might be like this is through the dynamical friction. So as the galaxy is stripping dark matter, it's stripping stars.
Yes.
Basically the same way. It's
Yes.
dynamical friction, and there's some tidal effects.
Yes.
I have another question for you. So if I understood the way you did the contouring surface brightness,
Yes.
and how I think most of these models do, whether they use lensing only or putting individual masses in brightness, they basically generate the same result. But in the ones where they're assuming mass distribution, it's isothermal.
Mm-hmm.
It's isothermal curvature. So in principle, if you identify, as you showed, that if you identify the galaxies and you walk the contours out of radius from those and you define it, in principle, you should also find that that's sort of isothermal as well, surface
Yeah. So in principle, the reason why we have been able to find this result in galaxy clusters is simply because the current technology with the limiting superbrains that we are able to trace, and also that's for one for the optical part, let's say, no? For the star part, and also from the point of view of how well they are able to recover the mass distribution, at this very moment of the history, we are able to do this very well in galaxy clusters. But in principle, this story is happening at all scales. It's happening also in our galaxy. So if we were able to see the stellar halo or in neighbor galaxies to such a level of detail of observing all this envelope, my bet is that they will distribute similarly to the dark matter as well. What is the problem? We are starting to scratch that from the optical point of view because we are starting to observe the halos and so forth. But imagine, so how do you reconstruct the mass associated to the galaxy? That's complicated, super complicated, because here they were using the gravitational lens, but around galaxies, gravitational lens is extremely unlikely and also very close to the center. So you're going to start observing dynamics, maybe the satellites and so on, and try to make a reconstruction of the mass of the galaxy, in the outer part. So answering to your question directly is, I expect that this is happening at all epochs and at all scales, but only now, it's only now when we are able to make it at such a level of accuracy to see that this is going on.
This is Jorge, and then we should wrap up, I think.
Somehow you addresses the issue that I wanted to say in the last question. I think that at small scales, I mean, at the center of the galaxies, they are very big. So at that scale, of course, they are going to be placing each other. And so, a suggestion is trying to see in your data by what scales you start to have problems. Things don't happen because in very small scale they cannot go together. So again, the question was about whether you expect to see something like that in galaxies, and I'm not so optimistic as you.
In the
and it's not necessarily because is that the history of the accretion is something that is very important for the dark matter, but it's not so important for the stars. So it depends strongly on the fact that you are observing this in class doesn't guarantee that you will get something similar to galaxies, because the way in which stars are produced in the halos and the dark matter ends up in the halo is very, very different. So
yeah, my comment would be that if we guarantee that what we are observing, the distribution of the star that we are observing, is dominated by the entire gravitational potential of the structure, for example, looking at the very outer part of the stellar halo, for example, and not into the galaxy where we have resonances, spiral arms, bars, and so forth that is affecting and also, as you say, the baryonic matter is dominating. But as soon as we guarantee that what is dominating is the dark matter and the gravitational potential associated to the dark matter, I can imagine that also the stars there would be following the same potential. Why not?
dark matter,
But give enough time for relaxation.
Dark matter is strongly influenced by the accretion process. So
Yes.
you have a string or something, whereas the distribution of
But
diffuse
that
light
stars far away.
have to do with the string matter.
Sure, but that stars far away from the disk of the galaxy are expected also to be connected to the accretion. So you cannot move a star from the disk to that region in a coherent structure.
The
Mhm.
dynamics play a role. And one example is, imagine something like the Centaur Europe, a galaxy that is dominated by rotation in a halo that falls into the Milky Way. Then you will see that basically the dynamical properties of the stars
That's right.
are different from the dynamical properties of the halo. And the relaxation times, which is important here, are rather long. So it means it will take a long time for that to reach the state in which you want to find it.
Yeah, that's the point. But in principle, give enough time to lose that history, and then you will just have a star following the gravitational potential.
I think we should stop here. Thank you very much. Let's thank the speaker again, Nacho, for a very interesting talk.